last time. Okay, so we're trying to develop a new way of dealing with multidimensional situations, so multivariable situations, by combining those variables into vectors. And as you can see, the end result of yesterday, well, in the middle, of yesterday, is how these vectors are combined explicitly with all the variables are hidden inside of them. Okay, so each of these terms, well, not each of them, but P, Q, and B, or each of them might have up to n or n being arbitrary number of variables hidden in them. Well, these are actually fixed. The only variable here is t, but these are like parameters, the initial position q, and the velocity, and all of them could be arbitrary. Okay, so the amount of data that is hidden inside of this little equation is unlimited. So I actually wanna do that before we go back to more like physics of what we started yesterday. Let's code this equation with Excel. Okay, so the equation is still say P is equal to Q plus TV. Okay, P being the current position, T is time, Q is the initial position, and V is that velocity. But think about it, it could be easily not two-dimensional, not even three-dimensional. It could be, the dimension could be any. So let me list here the variables. Say variable, and well, here say 1. It doesn't matter. So all these variables, maybe 1,000. So once again, we're thinking about abstract spaces rather than physical spaces, and so the variables could be prices or commodities, prices, stocks, whatever. And it is conceivable that we are considering some situation that when each prices are growing at a constant speed, but different rates, but at constant speed. Okay, so that's even complicated, and in the short term, it's probably reality. Some of them actually could be growing, some declining. And so let's just carry this out. So these are the numbered variables, so and they keep going. So that spreadsheet could really spread to the right. And then I'll put here the today's situation with say initial say Q. How should I write it? Equal, and let me put it in a bracket. And so I don't know, whatever the price of the commodity we're looking at could be. Once again, doesn't matter whatsoever. Okay, so this is Q. I put a bracket here, so to well, actually the other this bracket to indicate that what we're talking about is in fact a point in the 9-dimensional space. Okay, so then furthermore, the other parameter of the situation is the what is it? It is the velocity. So we're assuming that the prices that have been changing for a short period of time will continue to change for a short period of time in exactly the same manner. Okay, so I'll put the velocity here, and once again I will put it in the form of a, so this is a vector. Okay, so the prices might be small, might be large. How about 0? But also possible. Okay, so that is my velocity. So once again, the interpretation of this is, as I said, I missed one here. Okay, the interpretation is that say the second stock or commodity is worth $2 per share or whatever pound. And then it increases per unit of time, say maybe a day, but by 2. So maybe it is doubled for some. In some universe, the price is doubling every day. So that is the interpretation of well, I'm sorry, that's not it. And the current price is 2, and it's growing at 0.4 per, say, day. Okay, so that's the growth of that we have seen of this commodity, and that is pretty much a prediction of what's going to happen in the near future. And then we can create this single line in the 9-dimensional space. So the way we have done that already. So let me put t here. So starting with t0. Okay, so you realize then this is where I will be starting. So this is my t equals, not here, over here. T equals 0 is here. I'm going to repeat q. I'm going to repeat q, and then I will be developing from q at the speed of v. I will be developing down. Okay, so all right. So let me just copy, just for completeness sake. Okay, so I have copied the vector, the position here. I copied. Okay, now I will progress by, say, 0.1. Doesn't matter whatsoever. So the time increment for computations only, and for visualization will be, so the previous value plus 0.1. Okay, so 0.1 is the interval of time, and now I can put some different language here. So okay, so what do I write here? Okay, cool. So I need a formula, and what do I do? I compute the price of the first item, which was originally 1. What is the price now?
1.5.
1.5. Okay, so if I want to write a formula that will be applicable all the way down, what's the formula? The previous, yes, plus
0.5.
plus this one, right? Except I have to make a reference that is a correct way to make a reference, which will be R3C. Same column. So third row, same column. Okay, 1.5. Okay, let's confirm that if we spread it to the right. Okay, so these are the prices that will be 1.1 whatever hour or minute into the future of these commodities. Okay, so as you can see, they're developing slowly. Well, I probably don't want any negative prices, but that's not a big deal. Okay, and that is the end of it. Hold on a second. That's not. There's something which isn't right. It's not plus, but because it would be plus if the time period was 1, but the time period is 0.1. So I'm going to multiply it by 0.1. In fact, let me have an h somewhere. So let me put an h here somewhere. So I'll put h, the interval of time. I put 0.1 here, and here I will put instead of plus 0.1, I put plus row 2, C1, row 3, C1. Okay, and same thing I do here. I'm not referring to the time because it's just a marker, but I'm multiplying with it by the time interval. Every time the time interval is h, which is 0.1, so I'll make another reference to RC over here. I am referring to multiply this by R3C1. Okay, so once again, review the formula, even though it is tiny. But so the previous value plus the velocity, which is fixed, but your velocity, not the rest of them. Your velocity multiplied by the period of time. So each column is actually entirely one-dimensional. Okay, so the development is one-dimensional. Okay, so it is we have grown then by 0.05 rather than by 0.5 because the period of time was shorter. Okay, and then elsewhere, this is how things are developing. And then at this point, there's really nothing else to do. We wrote the formulas from the beginning correctly, and so this is, I could spread it as much as I like down. So in this particular case, I just, a few seconds down. And I could, now the point being now to, well, that's it. So that is the data is here. We have progressed a few days ahead, predicting what the prices will be, each of them. And you can imagine that we have 1,000 of those. If you want to visualize it, to convert that, actually, you might actually, another possibility is this is the data you're getting. This is the data you're getting, and you, for the price you want to make sense of it, that what you'll be looking for, you try to visualize it. How do we visualize things like that? Well, we try to plot it. You have data, and 2 columns at a time, unfortunately. So it's a 9-dimensional space, so there's no way for us to see the whole thing at once. So we look at 2 columns at a time. Okay, so if I plot these, so I insert scatter plot. Okay, so this is the scatter plot of the first pair of items. Okay, similarly, I could pick the next 2, and once again insert a scatter plot for those as well. Okay, so they look similar only because because Excel resizes it. Okay, but otherwise they certainly have possibly different slopes. But what is the meaning of these 2 lines? There will be, for any pair of columns in my table, there will be a parametric curve on the plane, which does not mean that's how many straight lines you've got. It means that there's a one line, and these are it's shadows. So there is a line in your 9-dimensional space, and then you pick one at a time. Pick 2 variables, which means 2 axes, which means a coordinate plane. Okay, so a coordinate plane. This one, for example, a 3rd and 4th variable coordinate plane. And then that line that exists only in 9-dimensional space or inside our head is being projected. A shadow is cast on that plane, and we see this picture. If we pick another pair of variables, it gives you another plane, gives us another shadow. So different shadows, as you know, if you cast light from different directions on an object, it might look different, but in this particular case, by design, it was supposed to be a straight line. We can only confirm now if we do more and more of these. Each of them will produce a straight line, and so we have then, in that case, we have all possible directions, and well, at least how many directions, how many pairs out of 9, a lot, and every time we look at it, it looks like a straight line. It is a straight line. Okay, so it is a straight line, even though in 9-dimensional space it takes a little bit of time. But since to accept that idea that it is still a straight line, but consider the fact that there's only one parameter, and that's pretty weird. Think about we are moving through space in time, and there's only one place for us to be in that space. So well, this is some kind of curve, and the fact that it's a straight line comes from pretty much observation, or once again thinking about the velocity being constant. So that equation reappears. This very compact equation might produce a lot of data. Not just 9 dimensions. You can have easily 100, or in realistic situations 10,000 variables dealing with at the same time. But there will be at every moment of time, there's only one combination of prices, and therefore it will be some kind of curve. It's not going to be a straight line really, unless you have some kind of nice theory to verify, but it will be still a curve. And so it's a parametric curve in a high-dimensional space. As you study, we're going to study it with the tools of calculus. Okay, so like I said, it is certainly a good idea to verify that every shadow does look like a straight line. Okay, so and that's just the beginning. That is the simplest parametric curve, where it is a straight line. Not only a straight line, it's incidentally, let me be clear. The straight line is really what we're studying here is not just a straight line. We are considering our motion along a straight line at a constant speed. at a constant speed, we're moving along a straight line, because you could move along a straight line at a variable speed. There is no trouble with that. You can even stop and turn back. So that line that we're seeing here is on its own does not really indicate how fast we are growing, whether it is a constant rate. You would have to include, instead of sort of spatial variables, you would have to include one time variable and one spatial variable. That way you'll see that it is a straight line. You're not only moving in a straight line, but also you're moving at a constant rate. Okay? So that is not only the simplest curve, but it's also the simplest interpretation of that curve, which is this. There is a slightly, you can imagine, probably a simpler, theoretically, representation of a straight line with a curve. If you're not just moving, you're moving not only at a constant speed, you're moving at a speed equal to 1. That will be the standard parametrization of curves that we'll be pursuing soon enough when we are interested in the curve rather than actual process. We are talking certainly about processes, whether it's physics, where it is or it is prices. It's a process. But really, sometimes we are studying the curve itself. So and then you can parameterize it in different ways, and one of them is the best, and that is when the speed of propagation is 1, and this is the speed of propagation is not 1, right? If you look at it, if v is what is the meaning of the v? If we forget about this one and we just look at the example that we looked at, what is the meaning of where is the speed? This difference between speed and velocity is clear.
Velocity has direction, speed is the absolute value of the velocity.
Well, we're not doing absolute value anymore. So it's magnitude of the vector. So in other words, over there on the right, that is our velocity vector here, somewhere 2, 3. And then if we would take its magnitude, and that would give us the speed. And the speed will be then 2 squared plus 3 squared, which is not 1. So we are moving at some meaningful to us speed through this line. But if we want to actually have the best parameterization, we'll pick eventually 1. So the speed of 1. Anyway, well, so we'll get back to that again. And now what we're doing is a little bit of elementary physics. And once we realize that this motion is a motion of a sliding body on along a straight line with no forces whatsoever affecting it, and there's no friction, there's no strains, springs, or gravity, and that's why there is nothing to change the velocity. And that is the second law of Newton. That is the acceleration is the force is acceleration times mass, which means that if and acceleration is the derivative of the velocity, so there you go. If the force is 0, acceleration is 0, which means that the velocity is constant, and vice versa. Okay, so and then we add forces. So once again, we start with a situation that we treat initially one direction at a time. So in dimension 2, we have a horizontal vertical motion. The vertical is more complicated because there's gravity, and then there's a horizontal motion which is not. And so there's no force, and we are pretty much in the same place as yesterday, and we have solved it. Okay, so separately, we also, and that is just like the way we did last time, we could point out that this is okay. So this is taken together. This is a parametric curve. So we can say that we have solved the problem. So it's almost okay. It's almost okay. But we're not going to leave it like this, just as we did not leave it in the yesterday, this one. So this is okay. You write it in the form either separately, which is what I'm referring to is one and the other. So you write how y is changing, how x is changing as a function of time. You have described the motion. You are fine. Okay, so it is just you are left with like calculus 1 point of view. Now we're doing calculus vector analysis, so we have to learn how to think in terms of vectors. So, and that's why we did this little computation, turning it into doing some vector algebra backwards. So we did first vector addition, and then we did scale multiplication. See factor t out over here, and that gave us really insightful formula for representation of a motion along a straight line at constant velocity. So similarly, we want to have this similar analysis here, so that once again we assemble everything into vectors and into one vector first, and then we're doing some little bit of vector algebra to take it apart, and then each term will have a meaning. Okay, and then we already started it. We detected the initial position, just like with the last example. Our initial allocation is right there if we just do some algebra. So we put the two functions separated by comma. Okay, but then we started separating it by sort of combining the terms that are closely related to each other. So the initial x, the initial y, we combine them together and we have initial location as a point on the plane. Then we combine what we did next is these two terms. I'm combining them together, and what do? And I combine them together because they're about the velocity horizontal and vertical. I put them together in one, and what I'm looking at is, in fact, well, it needs to emphasize that these are vectors. This is the initial velocity. This is the initial velocity multiplied by t as intended. We factor out t so that the units have become clear. It's clear that now these have the same units, say feet, and these units have the same units, that is, say, feet per second. Okay, and then the multiplication by t, the time which allows us to add these two together as vectors, because now with t the units do match. Okay, so what's the last term?
The vector 0,
0,
g over 2,
g over 2 t, right?
t squared.
Yeah, I think I want to take t squared out rather than just g over 2. 0 g and t squared over 2, like this. Okay, so it's slightly harder to understand these pieces. This one, it might take time, so this is time, but as it has, how much has passed since the beginning. T squared over 2 is, you can guess where it comes from. It's integration. When you integrate t, you get t squared over 2. That's how it happens. And we got to do both differentiation, integration of vector, not component-wise as we have one at a time, rather we're going to do the whole thing eventually. This time we're just trying to identify the pieces. So what's the meaning of, I'm sorry, I want to put g here. I want to put plus here, and I want to put negative g over there like this. Okay, so 3 terms are added. Initial location, initial velocity times time. The third one, some expression multiplied by t squared over 2. So can you tell what this is?
The acceleration.
It is the acceleration. You certainly could switch gears and express in terms of forces. It's just as good, but just as well. Suppose we already took care of that through second law of Newton, and we expressed, we turned the data about forces into the data about acceleration. Okay, so all right, so then let's, so that would be the end of the problem. The problem has been solved. We also usefully identify the pieces of locations and vectors of meaningful pieces that come from the setup of the problem. So if next time we approach something similar, we wouldn't go through these computations anymore, but rather look at where everything started. So we do not look at x separately and then solve problem in x as we did, and then y. No, we look at the meaningful pieces. We combine x and y into initial position. We combine the velocity with respect to x and y into 1, which is the initial velocity, and we combine the acceleration into 1 as well. Okay, so then and then if we do that, then the payoff is great because, well, let me just try to generalize this. Well, in what direction can we generalize this?
Two arbitrary dimensions.
Well, it is two. But I mean, if you want, we could add one more easily, right? So if we are now to switch to vectors altogether, then it won't matter how many dimensions you've got. It will be a vector. So for example, P naught is my initial location. What is the dimension? Doesn't matter. It will work in any dimension. Then I follow up with an expression that we are now recognizing as, I actually usually put T on the left as we have done scalar multiplication on the left. This is how I can put it. So far, well, let me put plus here. So far, this looks, you recognize this expression, right? This is the one. No, this one is. Initial location plus initial location plus the velocity times t. In that case, there was only one velocity, but you can say there was an initial velocity. In this particular case now, we're looking at the initial velocity multiplied by t, and then there's an extra term, but we wish we can help ourselves noticing that the terms are repeating. We are repeating it. We made things more complicated, and it did become more complicated, but these two terms are exactly the same as in that simpler situation. And then we're adding one more term, and and once again, dimension doesn't matter. We could just as well be doing this, like this. Okay, we could be doing it easily. I'm not sure what the meaning of the force would be in the, like abstract environment, prices, if there's any kind of analog in economics of the physical idea of force, I don't know. But certainly things match each other nicely. So, okay, I'll put t squared over to here. And what is this? Well, we just, let me put, say, A, the acceleration, which is a vector. Assuming, let me put 0 here to emphasize that we're talking about a constant acceleration. Location time is a coefficient vector times t. Let me put t squared over to my left. For some reason, I have been writing the multiples on left, number followed by vector. It's just a more comfortable. Okay, so that would be an expression of that vector representation of a curve, the curve of which remains unidentified so far, but we certainly could try to describe it. So this is a parametric curve of a uniformly accelerated motion. Through any space, okay, with specifically our initial position P naught, so initial set of prices, our initial velocity, so you detected how fast the prices are moving right now, okay, so that's P naught, okay, and thirdly, that is you have some kind of theory that you're testing. The acceleration is A. Okay, so the definition is arbitrary. Certainly, number one probably task would be switch to dimension 3 and see what it looks like. We could have done everything which is just the way exactly the same as before, but the advantage is already there. So if the axes may have been chosen ahead of time for some other purpose, and we cannot really modify them for our convenience. And the convenience is, as this example was chosen, so that our motion, horizontal motion, is in the direction of the x-axis. But you can imagine that even though the y direction might be vertical, the x directions might be not. Well, technically speaking, I would put z as a vertical direction. If I want to go with 3 dimensions, I have two horizontal dimensions x and y, and then the vertical direction is z. And then the z direction might be in any direction. Then I might be throwing not along x or y, but in some diagonal direction. And then in that case, the vector analysis of the final result will be much more convenient. So because you are not stuck with coordinates. So not only the dimension is arbitrary, also the choice of coordinates is arbitrary. And we are not necessarily throwing from the origin, and we are not throwing in any particular direction. You could just as well throw in this way, and then you have the x's like this, any weird way, and it will work out. This kind of a formula will work out just fine. So. Okay, so accelerated motion, then you can certainly, let me see, it wouldn't take us any trouble to generalize this, because I think we could do it quickly. So if I just, okay, so let's see, we have an idea of what's going on. So let's start to generalize. Let's start to generalize this into from uniform constant velocity motion to constant acceleration motion. Okay, but still 9-dimensional space. So let me enter first extra. Give an extra row here to place my acceleration. Okay, so my acceleration is. And then once again, I could put anything here, say 0, 1, 2, 0.1, 0.2, 0, minus 1. Okay, so that is my acceleration. Okay, so how do I modify my formula? So the initial, that is not going to change. This part is not going to change. It's still where we are. And then we could, fortunately, we already have the formula. So all we have to do is just change this. Okay, so in the way we have done it, we took the previous position and added something to the added the velocity times the interval of time. And now we know that we have to add yeah, unfortunately, the spreadsheet doesn't really. I didn't think ahead. So the trouble with applying this formula directly, is that it's not incremental, and we will have to actually look at the time. It is a disadvantage. It is the formula is there, so I could just plug in that formula. You would have to track if you want to do it incrementally, and this one has been done incrementally. So in other words, the next row depends only on the previous row and nothing else. So we're not really, in that example, we were not looking at, we're not applying that formula directly. Let me explain what I'm talking about here. And that's what spreadsheets are good for, is incremental computations. So this is what it is like. So P. Okay, so Pt is equal to, say, P naught plus V naught T. Okay, so that is the what the word is closed formula. But you can also have an incremental formula, and that is Pt plus 1, which is what we did, is equal to Pt. So the next location, well, plus h over here. The next location is the previous location plus V naught times h. Okay? So every time you progress, the velocity is used, multiplied by the time, and you have your next location. So the increment is v naught times h at every time. So that is the incremental formula, the closed formula, incremental formula. So this one, the second one is certainly better for spreadsheets, especially when the situation is more complicated than that. Okay, when, for example, we are not doing any integration, and we just want to collect the data and then just plug it one at a time, and then maybe the pattern of velocity might be unpredictable. So anyway, so that is not working out as well for the example of accelerating motion, because I have to keep track of, I should not only update the location, I also have to update that velocity. So just as well, let's discuss that quickly. So that is the constant velocity, and now constant acceleration. Once again, I'm writing my closed formula first. So it would be p naught plus v naught t, same thing, plus a t squared over 2. Okay? So acceleration is once again constant. That will be 0, just in case. Now, what is the incremental formula? It is uncomplicated. You just have to keep track of the velocity. So since acceleration changes the velocity, I have to keep track of the velocity. And let's write the velocity. So v of t plus h is equal to v of t plus what?
A times the quantity t plus h squared?
No, just h.
Oh,
Right? So because the acceleration is what is changing the velocity, and the acceleration is constant, which means that the dependence is linear, and that this is by how much at every period of time your velocity grows. Just like over there, the location was growing by that much at every period of time. Why? The formula is the same, because both of them it is a relation between the function and its derivative. So remember that the derivative of the location is the velocity, the derivative of velocity is acceleration. We just have done it only with the in one-dimensional case, or one dimension at a time, and now we're dealing with vectors, but the relation will be seen to be exactly the same. So, okay, so that is the closed formula then requires us to track both the location and the velocity. Okay, so that is how I write it from that point. Then pt plus h is equal to, so pt vth. So it's the same formula as above, except it's incremental, or in other words, is recursive. Okay, so this one is the difference is between this formula and over there is that the velocity is changing. So certainly this is accurate, and this one is approximate. Because this assumes that the velocity remains constant during that period of time. Okay, but for approximation purposes, especially for visualization, it works out just fine. So that is a good plan. The problem is it just does not fit easily into such a big spreadsheet. So I'm going to do this later. This plan, I'll follow it later when we do. Well, actually, that's what I did. Remember the first day of class? Visualization of the solar system, forces, all of that is here, and that's how it is visualized. Except you only track 2 dimensions, and that's why I was able to fit everything into a spreadsheet. And here I would have to have I would need to insert in between every row. I would have to insert the row for the velocity. It's a little bit cumbersome. So let me just do this simpler thing, and since the problem has been solved with the closed formula, let me just implement the closed formula, and we'll see what things look like, even though we probably can predict what it's going to look like. So I'll just write here the explicit formula, which is the initial position. So the initial. So that's the formula over here. So it will be, I will be just simply writing this formula over here. So initial position plus initial velocity times t plus the acceleration times t squared. Okay. So let me do that. So it will be the initial position, which is this one. So it will be rho 2c, okay, plus I take now the next one, which will be rho 3c multiplied by t, not h, multiplied by this thing. Which is rho c2, okay. And I'm adding one more term, which will be the acceleration, which is right here. So it will be rho 4c, same column, multiplied by the time, which is rho c2 over there, squared over 2. I think I got it right. Rho 2, yeah. Okay, spreading out. Some writing down. Okay, see, we computed, and as you can see, the shadow of that curve, it's still a curve, not a straight line anymore, but the shadows of that curve in the 9-dimensional space on the two of the randomly chosen coordinate planes are curves. And you probably can guess that these are quadratic curves, right? Because that's what we do. Okay, so all right. So let me just show you this one again. How we solve the problem the wrong way. This is old-fashioned way of dealing with it, but certainly works. But we have to learn really to take advantage of vectors. We have to do this from scratch, with vectors. So we'll see a few more examples of how we do that. But at this time, let me examine one more curve. That is really important, and that's the circle. The circle as a parametric curve. So it is the second simplest curve and just as important. Second simplest after a straight line, so it's a circle. And that's not a circle. So a circle. To keep things as simple as possible, we'll put it in the middle of our xy plane. And we put it a radius 1. Okay, so radius 1, center 1. Now naturally you remember this equation of this line. So of this curve, it is an implicit representation. There is no explicit representation because it's not a function. You would have to do as we did. For example, to either compute the length or to compute the area inside the circle. What did we do? Remember, we cut it in half, and then we were looking at this half and then that half separately. Fine. So that is an awkward way of doing things, and certainly we don't want to keep at it because the curve might be more complicated, and then cutting into pieces might be impossible. So that's why we want to have the circle as a parametric curve. Okay. The answer is very simple. Familiar, that's, if you remember this unit circle, you have seen it before. That is where all trig functions come from. So if I put t here, so let t be the angle. And we use this t, and this t is the parameter of our parametric curve. So remember how it follows, it goes from here. Trig functions, how do trig functions appear from this picture?
X is cosine t.
X is cosine t, that's right. So this is, we just look at the x and y coordinates of this point xy, the task we're after is to express xy, or x and y, in terms of t. And that's what it is. So if we go horizontally, that's x. X is equal to cosine t. And if we go y, horizontally, this time on the y-axis, this is y, and y is equal to sine t. Okay? Well, that is the answer. It's really not that complicated. So the answer is P of t, if I want to put it in the form of a parametric curve, one location, cosine t, sine t, or so that's location. If I want to think in terms of vectors, I could certainly do that as well. Say I could say, let me put it this way. How about it's equal to 0 plus? I'll show in a minute why this awkward writing is better than cosine t, sine t. Okay, so cosine t, sine t, instead of being a point now, it is a vector added to 0, which is the origin, or O if you prefer. So that's the O. Okay, so why do I do this? Because I want to do vector algebra with these, with that part. Okay, so the vector algebra, two operations, scalar multiplication, addition. Let's do scalar multiplication first. So what is the if I multiply by 2? So I have P of t equal to 0 plus, and that vector is multiplied by 2. What are we looking at? Equation of what happens to the vector if we multiply it by 2? This is a vector, even though forget about that, it depends on time, but it is a vector, and we multiply by 2, what happens to the vector?
Increases in magnitude
By a factor of 2. So, okay, so that vector over there, looking like this, with the endpoint xy, becomes twice as long, like this. So what does it do to the circle?
increases the radius to 2.
2. So this is a circle of radius 2. Okay, so all it takes is just to multiply that vector that defines our curve, our circle by 2. Okay, you can multiply by any number. Well, incidentally, if I multiply by negative 2, what's going to happen? What?
It's still going to be 2.
It will be the same exact thing. It will be the same exact thing, even though you might ask yourself, what is the difference?
Quadrant.
Well, so the initial point will change. It's the same curve, but parametric curves, they have beginning, ending, and they also have the direction. So the original one starts over here, and then progresses counterclockwise until it makes a full circle, and then keep going. The new one, it is here, starts at -1, 0, and goes clockwise. Okay, like this. And also at the same degree. So the last well, ask yourself, what if we start adding? If I add a vector, what's going to happen?
It's going to shift.
It will shift. Yeah. So we'll talk about that next time.